Thank you. Good morning still. My name is Will Payne from the University of Nebraska Medical Center, and I'll be giving my talk on computational methods for design of therapeutic agents. And to give you a little bit of background, I'm from the Department of Pharmaceutical Sciences, which means I'm primarily an experimentalist. So I hope you'll enjoy the mix of computational science with some experimental data as well in this presentation. All right, so the background on my project and why I'm using Blue Waters and why I'm doing any of this begins with my primary focus on nanomedicine, which most of you probably haven't ever heard about. But it's this idea that as an alternate strategy to developing new medicines or new therapies for cancer or other chronic diseases, we can take existing drugs and reformulate them to have better pharmacokinetic or pharmacodynamic properties. The idea is that we have some kind of macromolecular assembly, which includes anything from liposomes to protein drug conjugates or polymer conjugates, or even polymeric micelles, which is what I work with, to encapsulate drugs and hopefully get these drugs to the tumor or site of interest more specifically, more targeted, with a lower concentration of drug and decreasing things like side effects or other hazards. So the overall goal is to increase therapeutic efficacy and decrease any kind of side effects. A question that's come up multiple times, though, as I've been working in this vein of research, is what is a good nanoformulation? When we look through literature, there are literally thousands of publications on nanomedicine. Nobody ever compares them or even justifies why they're using given formulation or why they're using whatever components they're using, because it's very difficult to compare between one another. There's so many different metrics we could look at, but it's extremely difficult. So my entire project is essentially looking to come up with an answer to what's a good nanoformulation and how do I make a better formulation based on what I have. As I mentioned, the significance of this is that people have been working with formulations for a long time. This excerpt right here is from an article talking about the difficulty in translating advanced formulations into the clinic, just because they're a lot more difficult than coming up with a small molecule drug. So by coming up with some kind of metric or way to describe these nanomedicines better, hopefully we can move the field forward and get some more advanced formulations into the clinic. Now, prior work, before I began with Blue Waters, before I got this fellowship, I was entirely experimentalist. So my first project as a grad student was to develop this formulation of a mixed micelle to provide contrast in cancer models, both in MRI and fluorescence imaging. And as I was making this formulation, I noticed that I was having a lot of difficulties with the polymers that I was working with, the formulations that I was working with. Couldn't really explain why from a foundational point of view, but they resulted in low contrast and they were difficult to work with, and it just wasn't working out. And so I stepped back and I said, I need a better way to understand this. Looking at the results from that paper, essentially, I was able to show some contrast eventually by optimizing through a whole bunch of experimental methods, trying to get better signal, better imaging, but it really just wasn't that effective. So I really wanted some kind of theoretical approach to understand what can I do to make this better. And then building off that, another project in my laboratory that I've worked on extensively is drug loading and drug delivery. So it works the same for either contrast agents for imaging or for drugs for therapy. And this is one of the anti-cancer therapeutics that we use. It's called orlistat. It's extremely hydrophobic, so systemic injection doesn't work very well at all. You'll get crashing out, you get terrible side effects, things like that. So you wrap it up in a polymer micelle, and hopefully you get better PK/PD. However, when we did this, what happened was it took so much polymer to encapsulate this that the mass of stuff that we were injecting was simply too high. You couldn't get enough milligrams per kilogram of drug, per kilogram body weight to actually have a good therapeutic effect. So once again, this goes back to the fundamental physicochemical properties of what we're doing with the polymers. All right, step back completely and forget all about the translational aspect for a second. We wanted to go to the very, very basic level of what makes a good polymeric micelle, what happens, what are the things that I should be looking for. So all these wet lab experiments I did recognize that I need to first understand the basics of the single polymer systems. So when I design these polymers, how are they interacting with the solvent? I then moved into multi-polymer simulations, looking at how do polymers interact with each other and interact in the environment when they're making an aggregate. We can then look at simulations of dye and polymer systems to see we have this polymer, we have some molecule of interest, we load it into the polymer aggregate, then we can look at interactions between the polymers themselves, between the polymers and the solvents, and then between the drug-like molecule, small molecule, inside the polymeric micelle system. This is extremely difficult to read, I guess, because the resolution's low, but the idea is that with each different type of system, be it single molecule or single strand polymers, multiple strands with drug-like molecules, or a coarse-grained model of an entire micelle, we can gain all kinds of different information on the physical interactions that are happening in these big systems. And the key aspect, and the whole reason, justification for using computational methods to do this, is because we can quantify those. Experimentally, we can observe things in bulk solution, which I've done a lot of, but the nice part about using computational methods is that we can actually get quantitative information on the interactions and what's occurring, such as solvent accessible surface area, or hydrogen bonding between various molecules, be it the dye and the solvent, or dye and polymer, things like that. Those are all very simple tools that you guys have done extensive work. All the people in the field of molecular dynamics have done extensive work building out tools. And so they're very effective in this way. About a year and a half ago is when I started learning how to simulate things. So that was right before I applied for the Blue Waters Fellowship. I began looking at how to use GROMACS to simulate three very simple polymers. The polymer that my lab currently works with is called hyaluronic acid, and you'll notice that's the backbone of all three of these molecules. And so then we modify this with some kind of hydrophobic agent to drive self-assembly. In this case, you can't see the numbers, but it's hexane, dodecane, or octodecane, which are just long, simple strings of carbon atoms. So we can use those to start with a very simple first simulation. And then you look at what happens over time. You see over the course of time, these things collapse onto themselves. You get this kind of thermodynamically more favorable conformation where you're actually seeing a little bit of an association between the hydrophobic parts on the same molecule. Now, this is just a single molecule, single strand, so it's not super realistic to compare to real-world results. And I'll get to bigger systems later. But this was my first foray into actual simulations and learning how to do this. And then the next step was then to look at aromatic interactions. So can very simply look at broad differences between aromatic compounds and aliphatic compounds. And so over time, we actually built a library of different modified polymers. Now getting into the interesting part that actually has some real application. These are multi-polymer systems, and what we're looking at here is the self-assembly dynamics and what happens when we mix these polymers. And this sample over here is the octodecane modified hyaluronic acid. So that's one that's got a really long carbon chain, whereas this is the pyrene modified hyaluronic acid. So it's got a whole bunch of really aromatic groups, and that's where you can observe these pi-pi stacking domains. And the general observation is that when you have the long straight chain carbons, you get more tight packing. When you compare that to aromatic compounds, you get this pi-pi stacking interactions. And so it depends on what kind of interactions are going to work best for your analyte, drug molecule, whatever you're trying to load. The whole idea is that you can now think about the interactions and tailor the polymer that you're making this delivery system out of to your particular interaction. All right, so now that we've got multi-polymer systems, it's time to start looking at the interactions with some kind of drug-like molecule, some analyte, or something that we're trying to deliver. Now, I could have simulated this with doxorubicin or some kind of anti-cancer therapeutic that people commonly use, but instead, we chose to use fluorescent dyes. And the reason that we did this is because this is measurable with spectrophotometry. So you can look at UV-vis spectra, you can look at fluorescent spectra, and you can actually see what's going on inside the aggregates themselves. So these are hydroxychromone derivative dyes. They are all specially modified so that we can look at different types of interactions that are going on. So you'll notice that here we have long alkyl chains that will actually affect the way that it loads into the aggregate, and it'll also affect the fluorescent spectra. Same with phenyl substitution here as well, and then the dimethyl derivative as well. So the idea is that using different kinds of dyes that are more suited for different kinds of environments, we're looking for differences in the way that these dyes load so that we can kind of generalize and abstract what's going on inside our aggregates to help us inform what we might need for a particular functional group for a given delivery system. Okay, so moving on into the simulations of the dyes and polymers together, what we see is differences in most notably the hydrogen bonding. So if you have this hydrophobic molecule, in our case it's the dye, and it's loading inside of some kind of aggregate that's got very well-defined hydrophobic domains, you'd expect to see a difference in H bonding with the solvent from that small molecule, or in general with the polymer as well, but we focused on looking at the hydrogen bonding with the solvent. And I wish this was clear, but the idea is that we looked, this is the dioctane modified dye, and it's loading into the straight alkyl chain hyaluronic acid versus the diphenyl dye loading into the straight alkyl chains. And then we compare that to the aromatic modified, this is the pyrene modified hyaluronic acid, and you're loading, again, the same octane modified dye, comparing that with the phenyl substituted dye and the pi-pi stacking pyrene modified hyaluronic acid. And so what you can see is that there's dramatically different, I guess, ways that the dyes will load and interact with the polymers once you put them into the system. I mentioned that the whole idea behind this as well is that we can relate this back to experimental methods. So this is spectroscopy data on the loading of dyes into particles over time. And just as I pointed out on the last slide, you can see differences in not only hydrogen bonding, but with hydrophobic association. When you look at spectroscopy over time in a dialysis environment, you can actually see the spectra of the dyes change to reflect a more hydrophobic environment, that they're actually losing hydrogen bonds over time as the polymers assemble around them, kind of protecting them from the solvent. I'd love to go into more detail about this, but it merits its own presentation, honestly. So if you have any questions about solvatochromism or any of the special dye experiments that we did, I'd be happy to talk to you afterwards, as well as on my poster. So coming back around full circle and going back to the original problem, this is about the very first problem that I encountered, which was how do I get better contrast out of my macromolecular contrast agents? So using simulations and using the insight that I found from these simulation experiments, I've started designing a new series of contrast agents for cancer imaging. So the hope and the goal is that by having a slightly better knowledge of what's going on, we can design a little bit better of polymer, and that's why these ratios are calibrated. You can't actually read the numbers, but that's why these ratios are calibrated specifically the way they are, is to hope that using this insight that we gained from the simulations, we can actually make a better formulation. That's what I'm working on right now. And then the future work that's I'm kind of shifting into as well is a concept of generalization and abstraction. As I mentioned, the polymer that I've been working with this whole time was hyaluronic acid. And since it's a naturally occurring biopolymer, we get it as a genetically engineered product. It's very difficult to control how it's synthesized. So as a synthetic chemist, it's really not an ideal model. So I'm actually working with some collaborators to synthesize some new polymers that we're also going to model and try to generalize. The idea is that if we want to have a real impact in the field, if we want to have something that's broadly applicable, it needs to be generalizable. And to do that, we need something that's much more standardized, much easier to control on a molecular level. And the hope is that as we investigate these systems, we'll have something that other people can apply to their own polymers, their own analyte, whatever they're using, more so than what I've done so far. So in conclusion, go ahead and to wrap it up, the whole motivation behind using simulations was to help inform my experimental design. So I'm using simulations as a tool to help me come up with better ways to make cancer therapeutics or drug delivery agents. And while the simulations aren't incredibly complex, I think it's important to note that they're still valuable. So many people have presented very complex simulations, very awesome science, but it's nice to see that being very new at this field, I've been able to run simulations and actually get good information that help guide my experimental design. Additionally, this is what I consider a step forward in coming up with an answer to that question on what is a good formulation. By understanding the things like hydrogen bonding with the thing that's dissolved or contained inside the aggregate, to looking at what kind of functional groups we need to have on the molecule or the polymer, I think it helps us to get a fundamental understanding on the polymer level of what leads to a good formulation. And then finally, working towards generalization so that this can be applied to other people's research. So for acknowledgements, I, of course, acknowledge and thank my mentor, Dr. Mose, who's helped me guide through this research, as well as my lab members who have all had very valuable contributions, and our collaborator in Ukraine, who helped me to learn a lot of the simulation work, especially parameterization. And then, of course, the value of Blue Waters can't be understated, especially working with my point of contact, Robert Brunner, and the support staff. They've been very helpful as I've been learning the ropes. But I think another thing that merits mention with being a Blue Waters Fellow is the independence that I've been able to gain and to be able to pursue this problem. So originally, if I had not got this fellowship, I wouldn't have been able to do these simulations and to investigate this computational work. And it's led to essentially my own independent, I guess, vein of research that's complementary to my advisor and has led to follow-up fellowships as well that I'll get to continue this work over the next year or so.